We are still at the network layer and we will continue to be at the network layer for some more time. We looked at quite a few issues. We saw the IP service model, we saw the IP packet format, and then we looked into addressing and a lot of issues there, as well as forwarding. There are a few supporting protocols that help this entire process. One is Address Resolution Protocol, ARP. Another is the ICMP protocol. So that's the focus of this video. So when we covered forwarding, we needed this IP address to MAC address translation. This service is provided by the ARP protocol. Not only that, often it is also useful to debug the performance of the flows. For example, are the packets being dropped by the routers? If so, why are they being dropped? So this debugging is provided by this ICMP protocol. Not only this, it will also permit routers to communicate to the host about other things like the possibility of better routes, what kind of net mask to use, so on and so forth. So let's look at each in turn. So what does ARP do? Let me repeat the problem. We saw that the IP layer forwarding is based on the IP addresses, whereas the next hop delivery of a packet happens over a link, and this is based on link addresses, that is MAC addresses. Now we need to perform IP to MAC address translation, and the protocol that it does is called ARP protocol. It stands for Address Resolution Protocol. ARP is one of the simplest protocols that is out there. Given this, I want you to think clearly on how you would design such a protocol. For example, what layer would you make this ARP process run? And how do you ensure that the ARP process gets the relevant packet? So this is the problem of demultiplexing. And when these ARP messages are carried at a link level frame, what addresses should that particular frame carry? The source address, the destination address. What should be the content of the particular message? When would you send it? And how do you act when you receive a particular message? So think about it, design the particular protocol, and then proceed. So in reality, the ARP protocol operates at the link layer, but it does not do any framing or media access control. That is handled by the specific link layer technology, for example, Ethernet. So it is a companion protocol. For example, where if it were to receive a particular frame with a frame type equal to this, it will deliver that frame to the ARP process. But on the other hand, if it were to receive a frame type corresponding to 0800, this corresponds to the IP, it will deliver it to the IP process. But why link layer? Application layer is too much of an overkill. It really doesn't need to go through the transport IP, so on and so forth. And similarly, network layer is also too much of a overkill. You really don't need an IP layer header for the ARP messages. So you can manage with a link layer header. Now coming to the addressing to be used in the link layer frame, much like we saw in DHCP, here also you just broadcast this message. The message that you send within roughly translates to what is the MAC address corresponding to a given IP address. So this is the content of the message. And this message you are just going to broadcast. So all the hosts are going to receive this particular message that belong to the same physical network as the one who wants this particular IP address. And the host with the matching IP address is going to reply to this particular message. And what does it reply with? It basically tells this is the MAC address corresponding to this particular IP address. Not only this, each host, since it needs this information for forwarding, maintains a cache with this IP to MAC address translations. And the entries in this cache time out periodically. Why do you think you should remove the entries periodically? Well, for the same reason we saw when we were looking at the bridge entries timing out. What if the translation changes? The same Ethernet card now got a different IP address from the DHCP server. I will explain this further through a concrete example, but before that, let's look at the ARP packet format. So here is the ARP packet format. The first field is the hardware type. Basically, what link level technology you're using. So for example, if you're using Ethernet, you're going to set this value is equal to 1. The following field is the protocol type. So this refers to the higher layer. Are you using IP in case this field is set equal to this? Following this is the hardware length field. So it is specifying what is the length of the MAC address. In this case it is 48 bits, and it will also specify what is the length of the protocol address. In this case it is IP, thereby it is 32 bits. And following this is the operation, whether it is a request or a reply. Then you specify the source hardware address. Then there is field for specifying the source protocol address, and then you specify the target hardware address and the target protocol address. So henceforth we will use the term originator to refer to the host that is generating an ARP request, because it wants to know the MAC address corresponding to a given IP address, and target as the host that is going to reply to this ARP request. So it will do this, generate this ARP reply packet. And then there are these intermediate hosts which, based on what they observe, they kind of use a cache to refresh entries. This caching mechanism also I will cover shortly. So in this example, we have 4 different hosts connected via a switch. So they are forming some LAN. It could be an extended LAN as well. I'm just keeping it simple. Now suppose A wants to determine what is the MAC address corresponding to IP address of B. So that is what it wants to do. So for this, it is going to generate an ARP request. This ARP request has a MAC header, basically the Ethernet header. Within this MAC header, there will be a source address and a destination address. Not just this, this ARP request also has a payload, and within this payload, as we have seen in the packet format right here, so this is all the payload attached to that Ethernet header. So within this also, as you can see, there is a source MAC address, source IP address, target MAC address and target IP address. So the same I am mentioning here. Lot of people tend to confuse this with this. So don't confuse. So this is a separate header. This is part of the payload. Now when this ARP request is being sent, it has to be sent as a broadcast. So this destination address will be a broadcast address of this type. Within it, it is going to fill its source MAC as well as source IP. This are filled. So this one will correspond to A. This also corresponds to A's credentials. Target MAC it doesn't know, but it wants to determine the target IP of B. So this is the information that is going to be filled in an ARP request. Now this it is going to send it out, and the switch is going to broadcast it. So this packet actually goes out on all the links and everyone is going to receive this particular packet. Now we will come to the action at these intermediate hosts shortly, but before that let's see what B does. B processes this packet and knows that someone wants to know its MAC address. So the B is going to generate an ARP reply. With this also will have a MAC header corresponding to Ethernet header, and it will have a payload as well. In the MAC header, the source address will correspond to whose? Right, it will correspond to that of B. What about the destination address? Well, it could be broadcast, but since this is a targeted reply to A, the destination address will be the MAC address corresponding to A. Because there is no reason to believe that other hosts will be interested in receiving this particular reply. So it is a targeted, in other words, this is a unicast message, whereas earlier was a broadcast message. So this reply from B could potentially be directed only towards A if this already learned where A is. Now coming to the payload, in the source MAC as well as source IP, since this packet is originating from B, this will be B's source MAC and source IP, and the target will be A and target IP, this is MAC, will be A. So here, as you can see, all entries are filled. So now based on this reply, A will know that this IP address corresponds to this MAC address. In all this ARP operation, there is a cache that is maintained at each of the hosts. So when ARP request is generated and a reply comes back, this cache at this originator A will now have an entry that says B's IP address corresponds to B's MAC address. Similarly, the cache at B will, so this is A's cache, and the cache at B will also contain an entry that says A's IP will map to this A's MAC. It's useful to maintain this in B's cache because A is doing ARP to send some higher layer packet. Very likely B will have to respond to that particular packet. So it might as well know what the MAC address corresponding to A's IP address is. So this information is also maintained in B's cache. Now what do this intermediate node C and D do? So C and D, on receiving the ARP request, if they already have an entry for A, they are going to refresh this particular entry. In other words, each of these caching entries have a timeout, so they are going to reset that particular timer. If they don't have an entry, that is, they don't have no entry for A, they are just going to ignore this particular message. This is just to ensure that so that the ARP table is not cluttered. There is no reason to believe that C and D have to talk with A. Why put an entry? So they don't put this particular entry. Now what about ARP reply? Should C and D do anything about it? Well, C and D may not even see the ARP reply because, as I said, it is unicast, so they don't have to do anything about it. So all this is what is captured here. The originator, which is the generator of ARP request, will add the entry corresponding to the target, and the target will add a cached entry corresponding to the originator, and the intermediate host, only if they have the entries, will refresh, otherwise they will ignore the ARP request. And whenever it comes to forwarding a datagram, you just check cache to see if there is an entry. If there is an entry, you will use that entry to forward that particular packet. If there is no entry, you are going to invoke ARP to populate that entry. In Gracchus ARP, these are generated by a host to inform others within the LAN of its own IP to MAC mapping. That is why it is called Gracchus ARP. No one requested for it. It is itself telling everyone, see, this is my IP address and it will map to this particular MAC. So these Gracchus ARP are broadcast in the network, by which I mean in the MAC header, the source will correspond to the source MAC, that is, will correspond to whichever host is generating this particular Gracchus ARP, and the destination will always be a broadcast address. So this is something to keep in mind. Now remember, I mentioned that ARP, there are two types of ARPs, ARP request or ARP reply. So this Gracchus ARP can be generated as an ARP request or as an ARP reply. But the thing to note is, if it generates it as an ARP request, no one actually is going to reply to it because this is a Gracchus ARP. Similarly, if it was generated as an ARP reply, there was no one who asked for it. This guy is generating on its own. That is why it's called a Gracchus ARP. Within the Ethernet payload, in other words, the ARP message, there are the source and target MAC IP, so on. In this Gracchus ARP, what do you think the source IP is set to, and what do you think the target IP should be set equal to? Well, straightforward, since there is no other host other than the host generating Gracchus ARP, both the source IP and the destination IP is set to the IP of the machine generating Gracchus ARPs. The source MAC is also set to the MAC address of the machine generating this Gracchus ARP. The target MAC actually is a tricky business. It totally depends upon the implementation. In some implementations, for example Linux, this could be set to FFFF in case this is a request, and it is set to the MAC address of the host generating the gratuitous ARP in case it is a reply. But if it is Windows machine, it could differ. So this is up to the particular implementation of gratuitous ARP. So this is not well defined. Now, can you think of situations where such gratuitous ARP could be useful? Why do we want to do this? There are quite a few reasons. Whenever this IP to MAC address translation changes, you generate such a gratuitous ARPs. So this can help, for example, to rectify the cached ARP entries. Earlier you were associating a specific IP address with your MAC address, and now you got a new IP address and you need to clear out the ARP entries in part of the other host. So when you set a gratuitous ARP, they are going to take note of this new mapping. This feature also helps in detecting duplicate IP addresses. This is something you may have seen in Windows machines. Suppose a machine is manually configured with an IP address that is already in use by some other machine. So this machine who got manually configured, right after the configuration, it can send a gratuitous ARP saying that this is my MAC address and this is my IP address. Now some other host, because this is broadcast, is going to receive this particular ARP message and it will notice that the IP specified there matches with its own IP, in which case it will send an ARP reply saying that this IP address matches with my MAC address. In response to this, the manually configured machine may display a message that says duplicate IP address detected, thereby you will have to change your IP address. So this helps during the bridging process as well. For example, if one host were to move from one Ethernet segment to the other Ethernet segment, then the bridge has to change the port entry. So when it moves, if it were to generate this gratuitous ARP, it helps the bridge change the port information corresponding to this particular MAC address. So that's more or less with respect to ARP. Moving on to ICMP protocol. ICMP stands for Internet Control Message Protocol.